Okay, I'm out sick. My daughter is sick, so I got to go home and take care of her. But um, I wanted you guys to know that you have a quiz tomorrow on static equilibrium. So a problem where you have to draw a free body diagram. You have to balance the forces, balance the torques. Just a single problem on that. And then I wanted to show you guys how to use integration to find center of mass of an object. So that's what this video will be about. Video won't take the whole class, and then after I'm done, you'll have some practice problems on static equilibrium that you can spend some time working on to get ready for tomorrow's quiz. Okay, so we've seen center of mass, finding the position of the center of mass like this before. So the position of the center of mass is position of part 1 times its mass plus position of part 2 times its mass for as many parts of the system as there are, divided by the total mass in the system. All right, and the way that we turn this into an integration problem is, or what it lets us do is, instead of thinking about something that's a bunch of discrete bits like this, where we want to say find the center of mass of some system of objects that looks like this, is now we can take a continuous object like this and break it up into a bunch of tiny chunks, each of mass dm. So like this bit of this rod, for example, would have mass dm, and then we can just essentially add up an infinite number of these chunks. So the position of the center of mass would be given by position 1, let's call this little chunk 1 and 2 and 3 and 4, position 1 times its little bit of mass dm1 plus position 2 times its little mass dm plus position 3 dm, and so on, all over the sum of all these little chunks of mass dm1 plus dm2 plus dm3. And what makes this an integration problem is that we're going to let dm go to 0. So we have an infinitesimally small bit of mass of this rod, and then we're going to sum up an infinite number of these things. Just like in an integral, you kind of find this, the slope of dx represents an infinitesimally little small bit on the horizontal axis. Okay, what makes this new is that when we've done integrals in the past, say for example, integral of x squared dx, x squared is kind of seen, it's kind of, we don't even talk about it, but it is on coordinate axes. So we integrate, and when you integrate, you can find the area underneath it. And we don't even really think about this, but you can really only integrate on a coordinate system like this. And so the question becomes, you know, like if you talk about something in terms of mass, dm, it's hard to do unless we can plot the mass on a coordinate system. So let's just do an example so you can see like how we're going to put mass on a coordinate system so that we can integrate it using the old tools that we have. All right, so first of all, let's rewrite the definition in the integral form. So we're looking at this thing, and we're thinking about how what we're really doing is we're summing up all of this stuff on the top. We're summing up all that stuff on the bottom. Well, the sum of the bottom is really easy. The sum of all the little chunks of mass, dm1 plus dm2 plus dm3, that's just the mass of the rod. So let's call that, what's rod here? Here's our rod that we're trying to integrate to find the center of mass of. Let's just say that this thing has mass capital M. Okay, so we have the position of each little bit of mass times its little amount of mass. We're going to sum up an infinite number of those. That's our integral. And then we're going to divide that by the total mass of the rod m. So that m is a constant. We can just bring it out in the front. And here's our definition of the location of the center of mass using the integral form, x m. Okay, so now we're onto this part here where we would need to get dm into like coordinates so that we can kind of plot out the mass of this rod on a coordinate system. So let's just stick the rod on a coordinate plane. All right, it's a thin rod, so it really has no height. So here's our x-axis, here's our y-axis. And this rod is a uniform rod, so it has the same mass for every little chunk, and that's easy to define. So lambda is the symbol for this thing, and it's going to be called the linear mass density. And it's really no different than regular old density, you know, grams per cubic centimeter, except for this one, we don't really have to talk about cubic centimeters. We can just talk about grams per centimeter because it's just got one dimension. So we'll define it as the total mass of the rod, m, divided by the total length of the rod, which we'll define this distance here. Or if this is 0, then this would be position L. So m over L represents this linear mass density. And for this uniform rod, this is a constant. No matter what centimeter of this rod we talk about, it's going to have the same number of grams per centimeter or same number of grams per meter as any other bit of this rod. Okay. So if we want to find the mass of a small chunk, dm, you could look at this lambda this way. Like, let's say we had a rod that was 2 meters long and had a mass of 6 kilograms. Lambda would just be equal to 6 kilograms over 2 meters, so 3 kilograms per meter. So if there was a rod that was, say, L was half a meter long, to figure out how heavy it is, we would just have to multiply L times lambda. 0.5 meters times 3 kilograms per meter gives us 1.5 kilograms. So if we take the length that we have and we multiply it by this constant, the linear mass density, then we can get the amount of mass that we have. So if we're trying to find the mass of this little chunk of dm, all we have to do is multiply dm, or whatever length we're interested in, by lambda. Okay, so if we think about this chunk here, for example, right there, I want to figure out the mass of this thing. To get this on a coordinate system, it's on our x-axis. So what's the length of this little chunk? Well, the length is dx. So dm is going to become lambda, that's our constant, times the little length dx. And so that's dm. And then this, in our definition, our integral definition for center of mass is right there. So now let's write this full integral out in a coordinate system instead of trying to integrate over masses. So x times dm, which we just found is going to be equal to lambda times dx. Okay, now this integral is going to be pretty easy to do because lambda is a constant. So lambda we can pull out to the front. So lambda over m integral x dx. All right, and we're going to integrate over the whole length of the rod, which we said was 0 to length L. Okay, so lambda over m, that all stays out in the front. Integral of x dx becomes 1/2 x squared, and we have to evaluate that from length 0 or position 0 to position L. So lambda over 2m, bring all the constants out in the front, and then we have x squared from 0 to L, lambda over 2m, L squared minus 0 squared, so we get lambda L squared over 2m. Okay, so if you recall where we started, this is a uniform rod. I already know where the center of mass is, and you should too. So let's make sure it ends up where we know it should. It's got to end up at this point, the midpoint of the rod, L over 2. Okay, so let's plug in what we know. We had said in the beginning, the way we defined lambda was the mass of the rod divided by the total mass of the rod over the total length of the rod. If we plug that in, we get m over L. I'm plugging it into here. So that's lambda times the length of the rod squared over 2m. This m cancels this m, this L cancels the square, and we get exactly what we thought we should, L over 2. Okay, so why would you integrate to find the center of mass of that rod? Well, you wouldn't. That's just to show that this definition, this integral definition of finding the position of the center of mass matches what we had found before. So our new formula, and you don't have to use this all the time. If you know where the center of mass is, then there's no point in this. But if you don't know where the center of mass is, and you have a object that you can't treat as just the sum of a bunch of discrete points of mass, then this is what you have to do. So let's look at an example where we use this again, this new integral definition of the center of mass to find the center of mass. Okay, there it is. Let's take it to the next page and let's integrate to find the center of mass of a triangular sheet of uniform material. Okay, so let's say we have this sheet, this triangular sheet of material, and it's all the same thickness and it's all made out of the same stuff. It's 30 centimeters long. So the triangle is 30 centimeters long. It has a base of 20 centimeters. And let's say that this thing had a mass of 800 grams, and we're trying to locate the center of mass of this thing. Okay, now it's symmetrical top to bottom. So we know just by looking at this thing, or we know by inspection, that the center of mass is going to lie along this line. We don't have to integrate to find that. We can just look at it. But we can integrate to figure out where along that line the center of mass is. Okay, so let's set up that integration. From the definition of finding the location of the center of mass, it's going to be equal to 1 over the total mass times the integral of x dm. Okay, so what does the little tiny bit of mass dm look like for this thing? Well, that's where these types of problems can get a little tricky. The more of them you see, the better you're going to be at selecting the little mass element dm to integrate over. So for this one, I'm going to look at vertical slices that look like this and say, okay, this little slice here represents the little bit of mass dm that's going to go into this calculation. And then I'm just going to add up all of those little bits of mass from the point of the triangle all the way down to the base of this triangle here. Okay, so we need to write that little bit of mass dm as some function on a coordinate system. So it's a little bit different now because our rod before had no height. It was just a length. Whereas now you can see as we go to different slices into this triangle, they're going to have different heights, they're going to be different masses, because as you go towards the bottom, they're going to be taller slices, they're going to be heavier, whereas a slice over here is going to be really short, it's not going to be very heavy at all. So we need to write a function that describes that relationship. Okay, but before we took the total length of the rod and divided it, or total mass of the rod and divided by the length, this time, so that gave us what we call the linear mass density. Now we're going to define something called the surface density. I have an area here that I can find. So the area of this triangle is just 1/2 height. Okay, so if we put the numbers in, the base of this triangle is 20 centimeters. The height of this triangle is 30 centimeters. So the area of this triangle would be 300 centimeters squared. And the mass of this is 800. So sigma is the symbol for the surface density. So how many grams per square centimeter as opposed to grams per centimeter, which is the linear mass density versus the regular old density, gram per cubic centimeter. So this will be defined as the total mass divided by the total area of this thing. So 800 grams over 300 cubic centimeters. Oops. That's regular density. We need square centimeters. So that is 2.67 grams per centimeter squared. So no matter what area I define on this thing, all I have to do is take that area, multiply it by this surface mass density, and I will know how much mass I've got. Okay, so now let's go back to our vertical slices here. How much area does this vertical slice have? Well, if I know the width of this thing, I know the height of this thing, here, the width is going to be dx. That's a big surprise. The area of this thing is going to be the height times dx. And the height of this thing is going to depend on our location x. As you can see, if we move to different x's, we're going to have different heights, like we said before. So we can write this out as a function using tangent. Right, so the tangent of that angle theta defined in the picture is going to be equal to the opposite side of our triangle, which we'll say is the height over 2 over the base of the triangle, which is going to be our position x. So let's just solve for h. X times sorry, I just had to pause there for a second. We have x times the tangent of theta times 2 equals h. And theta is not a variable. Theta for this triangle is defined. So we could just look at the total triangle there. Theta is going to be opposite, which we know is 10 divided by the adjacent side, which is 30, and that's a constant. So tangent of theta for this triangle is just going to be 10 over 30, or 1 over 3. So we could just put this in here in place of the tangent of theta. Just looking ahead, you know, like we don't want to integrate a tangent, but it's not a big deal in this case because tangent of theta is not part of the function. It's just another constant out in the front. So I gotta erase this. Hold on. So 2x times 1/3 the tangent of theta. That's the height. And remember, the whole point of this little diversion here was to get an equation for the area on the coordinate system. So the area is going to be equal to 2/3 x times the width of this thing. So this is the height, this is the width, that's our area, And now we can write out dm on our coordinate system. So dm is going to be the surface mass density times a little bit of area, EA, or let's do it the way we had so our surface mass density times this area that we just found here, so sigma times 2/3 x dx. And now we can put this into our center of mass integral. X times dm, which is this function. So sigma times 2/3 x dx. Okay, sigma is a constant. You can pull that out to the front. Integral, we have x and x. Suppose we could have pulled the 2/3 out as well. We have 2/3 x squared dx. Now, what are the limits of this integration? Well, we're going on the x-axis, so we're going to integrate from 0 out to 30 centimeters. That's going to get us all of our vertical slices in this triangle. So we're going to integrate from 0 to 30 centimeters. Okay, so now this integral is pretty easy at this point. The integration is not the hard part, it's the setup. So pulling the 2/3 out to the front, we're just integrating x squared dx. So that gets us 1/3 x cubed. We're going to evaluate that from 0 to our final x position of 30 centimeters. Okay, so finish the integration, then we'll plug in the numbers and see where it lands us. 1/3 times 30 centimeters cubed minus 1/3 times 0 centimeters cubed. This is just 0. So what do we get? 2 sigma times 30 times 30 times 30, which is what? 27,000 centimeters cubed all over 9m. Now we can plug in our sigma and our m. Sigma, recall, we had figured out way earlier. It's how many grams per square centimeter, so 2.67 grams per square centimeter. Times 27,000 centimeters cubed divided by 9 times the total mass, which was 800 grams, gives us a value of, gives us a location of 20.0 centimeters. And I just want to point out, if you look at the units, this is a good sign that we're finding a center of mass, and we end up with units of centimeters only, because we have on the top grams per centimeter squared times centimeters cubed, all divided by grams. So these centimeters squared are going to cancel 2 of the 3 of those. And then this grams here is going to cancel this, leaving us with just centimeters, which is what you would expect if you're trying to find the location of the center of mass. That should be reassuring that something that happened in our integration is probably right. It's not a guarantee, but it's definitely a way to find a mistake if you made one by doing some dimensional analysis here. So this says that the center of mass is located at 20 centimeters. If we go back up to this thing, 30 centimeters, 20 centimeters in, it ends up about 2/3 of the way down from the tip of this triangle. And physically, that should make a bit of sense. More of the mass is located on this side than this side. So we would expect it to be to the right of the halfway point, 15 centimeters. So Those are all good signs. Okay, so let's just recap here. Ideally, I would have been here today so that we could talk through this together. And my plan was to have one of these integrations on tomorrow's quiz, but without the chance to kind of have a conversation with you guys about it, it's not going to be tomorrow, but it's going to be soon. So I just want to recap the keys to finding center of mass by integration, and ask you to, if you're totally confused, to watch this video one more time so that we can talk about it after your static equilibrium quiz, which is tomorrow. So first is, you have to know this integral. So to find the center of mass, we're going to do 1 divided by the total mass integral of position of the little chunk of mass times its mass dm. And you're going to integrate over the whole mass of the object that you're interested in. Okay, so that's the first key, know the definition. Second thing is dm is not really an we can't really integrate over masses. So what you have to do is you have to write out the mass of the object as a function of location. So dm, we're going to turn this into an equation on a coordinate system. Ooh, there's only 2 O's in there. And this is the part that's tricky, especially if it's the first time you've seen it. So we'll look at a couple more examples, but let me just remind you what we did. For a rod like this, we essentially said, let's define a constant that we called the linear mass density. And we said that that's going to be equal to the total mass of the rod divided by the total length of the rod. Okay, and then here, any length that you have, and our length is going to be dx or dl, you just take this lambda times dx, then becomes our little mass chunk dm. And this is something we can integrate over all the x's in that rod. For something that was a surface, whatever shape it is, ours was a triangle, and just a circle here, we can define something called the surface mass density. Surface mass density is, you guessed it, the total mass divided by the total area. And then what we can do here is we can write a little chunk of mass as surface mass density times a little chunk of area, dA, is going to be equal to dm. And we were clever about how we defined this little chunk of area in the triangle that we integrated. We said, oh, let's just look at vertical slices like this, so that then we can say, if we can write a function for the height of that thing, then we can just multiply it by our variable dx and integrate over that. So we turned in our surface area dA as some height function times dx. So we did sigma times some height. Height was a variable. We had to write it in terms of x, and that becomes our dm. Okay, but this is the key here, is you have to somehow write out the mass as a function of the location. And then that's the key, that's the real heart of these problems. That's the hard thing to do. That's the thing that takes practice. And then you just do the integration. And that integration is the easy bit. That's the part where all of your hard work should pay off. If you're looking at an integral and you don't know how to do it, chances are there's something wrong with the setup, or we weren't clever enough in terms of how we set it up to actually get an integral that we could do. Okay, this is the intro to all this stuff. We'll review it together when I get back. The remaining time you can use to work on static equilibrium problems that Mr. Szymanski should pass out. Okay, see you tomorrow.